This is 7.5.4, Faraday's law. Now, we did a demonstration earlier where we took a magnet and moved it in and out of a coil of wire connected to a galvanometer, and we saw that while the magnet was moving, we had an induced EMF in the coil. If we stopped moving the magnet, then the induced EMF disappeared very quickly. So that shows us that the induced EMF is equal to the rate of change of flux linkage. So when the magnet was moving, flux linkage in the coil was changing, and as it changes, there was an induced EMF. So that's our first definition. Faraday's law says that the induced EMF is equal to the rate of change of flux linkage. Put a box around that. And so the equation that describes this is EMF is equal to, because n, the number of turns, that's just a constant. So if you were to differentiate n phi, the n can just come out. So EMF is equal to n d phi dt. Now, interestingly, there's a negative sign here. So it's minus n d phi dt. So epsilon is our induced EMF, measured in volts, and phi is flux in Webers, and t is time in seconds. Now that negative sign refers to Lenz's law, which we'll talk about in a moment. And that basically means that the induced EMF tries to stop you from making that EMF. It opposes what is creating it. So the induced EMF tries to stop the change that induces it. And because it tries to stop, we then know that work has to be done in order to generate electricity. So we cannot generate electricity for free. We'll do an example quickly. So I'll draw some coil of wire, like so, and I'll draw a magnetic field where the flux density is 4.0 times 10 to the minus 3 Tesla. We've got 50 turns of coil, and the area is equal to 0.02 meters squared. So we can say if the field is reduced to 0 in 0.2 seconds, what is the induced EMF? You can pause the video here to try the question and resume the video when you're ready to see the solutions.
So when you say if the field is reduced to zero, do you mean like rotate the 50 turns to make
Doesn't matter. So to solve this, we know, first of all, that the field starts with some value. So if it begins with some value, there is some value of flux linkage before. And then there is some value of flux linkage after, which takes 0.2 seconds to happen. So the change in flux linkage is just whatever the flux linkage was, and it drops down to 0. So first we find delta phi, or n delta phi. So n delta phi is going to be equal to the original minus what it ended up becoming. Or the final minus the original, rather. So the change is 0 minus BAN, which is equal to minus 4 times 10 to the minus 3 times by 0.02 times by 50. And then the change in time was simply equal to 2 seconds, or 0.2 seconds. So if we put that all together, EMF is equal to minus n delta phi over delta t. So we've got minus 50 times by minus 4 times 10 to the 3 minus 3 times by 0.02 all over 0.2 seconds. And that gives us a value of 0.02 volts. Because the two negatives, they cancel each other out. So in this case, we had our flux reducing. So the change in flux was actually negative. Because the change in flux was negative, the induced EMF was opposite to that. It was a positive EMF that was induced. Now we can apply Faraday's law in different ways. And this is generally called the generator effect. So before we had what was called the motor effect, where some magnetic field caused a force to be induced on a moving charge, which is a current. But in this case, we're going to induce a current by moving the objects. So start with a uniform magnetic field going into the paper. And then I'll draw a wire that has a length L within the field. And what we do is we move the wire with velocity v. So move wire with velocity v. Now, as that wire moves, it's going to cut across the field lines. So imagine the field lines as arrows. If we move that wire down, it's going to cut across those arrows. So you can imagine as it chopping the arrows. And if it's cutting across the arrows, then the flux is changing. And if flux is changing, then there is an induced EMF. And we can figure out the direction of the EMF by using Fleming's right-hand rule, which is the generator effect. So you do exactly the same as left-hand rule. However, now we're going to find the direction of the induced current. So in this wire, for example, we've got F as our thumb, and because the wire is moving down, we put F going down. So our thumb needs to point down. Then B, which is our index finger, is going to point into the paper. So when we do that, we can see that the induced current is to the right. So the generator effect, use Fleming's right-hand rule. So current is to the right in this example. And the equation that links that is EMF is equal to BLV. So let's explain where this equation comes from, BLV. How would you work out the velocity of a moving wire? Let's assume it had constant velocity. What's the easiest way to work out its velocity? Right, we do distance over time. So let's say after some short amount of time, that wire ends up over here. So the distance moved by that wire is this red line. I'll do a dotted red line as these are all imaginary lines. So we've got S. Again, let's change that to red. So that's S, the distance it's moved. And it's taken some time t to move by that distance. Yeah? And just for visually, I'm going to draw another one on this side to represent that. So, if we look at this wire, the area traced out by the wire is equal to L times by S. And V is equal to S over T. So EMF is equal to BL S divided by T. And L times S is equal to A, which is the area that's encompassed when that wire has moved along that field. So we can see that creates some area. So that wire has swept an area within that field. So L times S is an area, so it's BA over T. Well, what was BA for a coil? That was the flux. So that's equal to phi over t. So again, we've gone back to it being the rate of change of flux. Let's do an example. An airplane with wingspan of 50 meters cuts through the Earth's magnetic field at 600 kilometers per hour. The flux density is equal to 6.0 times 10 to the minus 5 Tesla. What is the induced EMF in the plane? So pause the video here to attempt this question, and then play the video when you're ready to see the solutions. Okay, to solve this question, we're going to use the equation that was provided above. So we start with the equation, EMF is equal to BLV. So the flux density is 6.0 times 10 to the minus 5 Tesla. The wingspan is 50 meters, so we times that by 50. And then the airplane is flying at 600 kilometers per hour in this field. So we have to convert that to meters per second. So to do that, we're going to do 600. Take care of the kilo first, so times 10 to the power of 3. And then divide that by how many seconds are in an hour, which is 60 squared. And so that gives us an induced EMF of 0.5 volts. Now, we can induce an EMF in a coil in multiple ways. So I'm going to give you two ways of doing that. We can, one, push the magnet through the coil, or we can rotate the coil itself. So let's start with pushing a magnet through a coil. So we'll do a before and after. So we'll do a little magnet that's got a north and south, and we'll do the same magnet again below, north and south. In the beginning, we'll draw our coil somewhat far away from our bar magnet. And so if we just do the field lines coming out of the end of the bar magnet, we can see the flux going through the coil. And in the after scenario, I'm going to draw the same coil right up against that bar magnet this time. And then we'll just draw the field lines again. And we can see that much more flux now passes through the coil. in either case, the coil, the wires of the actual coil are cutting through lines as those lines are moving. So either the coil itself can cut through the lines or the lines can cut through the coil. If that cutting is happening, they're basically overlapping each other as they move, then there is a change of flux. So you can see as well, if we did rotation of coil, we'll see similar results. So we'll do before and after. So we'll draw our magnets again in the same way, north, south, north, south. And we'll draw the coil in the first example as facing towards the magnet so that the flux lines go through the area of the coil. Now, as we rotate that coil, so that it's sideways, in this situation, the flux lines pass parallel to the coil. So that gives us 0 flux. Because if you were to draw an indicator on that coil at the bottom, the indicator, you could draw it as either into the paper or out of the paper. So if I were to draw it out of the paper, say directly in the center, that arrow coming out of the paper and the flux in the center, well, they're at 90 degrees, aren't they? So if they're at 90 degrees, then there's no flux. And in the case of the before scenario, we can draw the indicator as coming out like so. And in that situation, it's at 0 degrees to the flux. And so therefore, there's maximum flux in the beginning. So if you're rotating from the beginning to the end, in between that, you're changing the flux from its maximum value all the way down to its minimum value. So it's maximum flux in this position. And then to go from the before to the after, we rotate coil by 90 degrees. And then you just keep repeating this process of rotating the coil. If the coil carried on rotating, another 90 degrees, another 90 degrees, the flux will go from maximum to minimum to maximum to minimum. However, because it will be the other side of the coil now facing towards the magnet, the induced EMF goes from positive to negative to positive to negative. Yeah? So that leads us on to Lenz's law. Let me start a new page. So Lenz's law says that the induced EMF is in a direction such that it produces a current that induces a magnetic field which opposes the change that induced it. So whatever we do to create an EMF or a voltage, that voltage creates a current in a direction that tries to stop us from creating that voltage. So it's not for free. So if we have a galvanometer, and some coil of wire, and we push a magnet through that coil of wire, we have to think about both the field lines of the north and south side. So in the beginning, it's the north side of the magnet, those flux lines are going to be the first to cut through the coil. And the north side of the magnet has flux lines which point outwards. They point downwards, away from the north. When the magnet is halfway through the coil though, the north side's flux is no longer going to be cutting through the coil, and instead it's going to be the south side's flux cutting through the coil as the magnet leaves the coil. And the flux lines of the south side point in the opposite direction to the side that the north was. So the south side's field lines will be opposite. So as that falls, we see the EMF change in such a way. So the EMF will increase, and then it will become negative and then decrease. And the largest change of flux linkage occurs when the magnet is closest to the coils. So in other words, the magnet is actively falling through the coils. Okay, let's look some more at a rotating coil. So I'll draw some field lines, and I will draw some coil which is at some angle, and I will also draw its indicator, which has some angle theta. Now the flux linkage is n phi equals to BANω cos theta. But if the coil is rotating, if our coil is rotating, then our angle is not constant. The angle changes. So we recall from circular motion that theta equals to omega t. So theta is equal to omega t. So n phi equals to BANω cos omega t. And EMF is equal to minus n d phi dt. So we need to differentiate that equation. So BA and N, they're all constants. So if we differentiate cos, what do we get? We get minus sine. So EMF is equal to minus sine, but then we also have a negative symbol here, so the two negatives will cancel out. So that becomes BAN sine omega t. But we have to apply chain rule because omega t is also a function of time. Yeah? So if we apply chain rule, omega t differentiates to omega. We're assuming that it rotates at constant angular frequency. So we get BAN omega sine omega t. So now, this tells us two things. Number one, that the EMF depends on how strong the magnetic field is. It depends on the area of the coils. It depends the number of turns in the coils. It depends on omega, which means how quickly the coils are rotating. And it depends on, at that snapshot moment in time, what position that coil is currently in. So in other words, if it's a function of sine, the EMF is not constant. The EMF is oscillating. And sine has a range from +1 to -1, which means that we're inducing an alternating current, not a direct current. So we'll write the equations out. EMF is equal to minus n d phi dt, which is equal to BAN omega sine omega t. Which can also be written as EMF equals to BAN omega sine theta. So if we were to sketch this on a graph, EMF, we get a sine graph. So the induced EMF is sinusoidal, which means it's an alternating current. And if I sketch field lines once again, so we'll do B. If we drew a coil and coil, and I also draw its indicator, draw it here. So in this side, we've got a right angle. So theta equals to 90 degrees. And here, theta equals to 0 degrees. So during its position, during a rotation, when theta is 90 degrees, we've got maximum EMF. And when theta is at 0 degrees, we've got 0 EMF. And that is the end of 7.5.4.